Okay, Unit 4 progress check for response numbers 10, 11, and 12. These are a little more challenging, maybe a lot more challenging than the first three, because you're talking about including different units, you're talking about including different skill sets that you couldn't include in units 1, 2, and 3. So the deeper we get into these unit progress checks, the more involved they will be. All right, so here's the question. From the time 0 to 10, and by the way, that will mean this will be a little bit longer video. From the time 0 to 10 included, water is flowing into a small tub at a rate given by the function. So when you're doing these types of things, it's important for you to recognize what the big information is. So from 0 to 10 included, into the tub, function defined by f, and then here's the function. Now this is a calculator problem, so the first thing we want to do is to put that into our calculator under y equals. Arctan is tan inverse, and I want to do this as simply as I can. So when this is pi halves, I prefer to avoid fractions, so I have 0.5 pi minus x over 10. So there's our calculator problem. Secondarily, it says from 5 to 10. So notice this function, that the into the tub is from 0 to 10. Leaking from the tub, leaving the tub, is from 5 to 10. So the tub from 0 to 5 is just being filled, and then at 5 minutes, it starts to leak. Okay, and then again, this is the rate. So again, I'm putting this equation into my y equals. All right, both f and t and l and t are measured in cubic feet per minute, and t is measured in minutes. The volume of the water in the tub is given by W. So at that point, we need to understand what it means that the volume of the water is the accumulation of the water, or the accumulation and the leaking combined. So for the first 5 minutes, it's simply the accumulation. For the full 10 minutes, from 5 to 10, it's both. It's the F, which is the water flowing into it, minus the L, which is the water flowing out of it. Okay. Okay, so then it goes into this question right here. At time t equals 3, there are 2.5 cubic feet of water in the tub. That means W of 3 equals 2.5, the volume, the total volume. Write an equation for the local linear approximation. So we're looking for slope and looking for xy at t equals 3, and use it to approximate the volume at 3.5. So we're talking about linear approximation here. Don't overthink it. Don't freak out. We need a linear equation, and we need an xy coordinate point. So going from here, we know they just told us that W of 3 equals 2.5. So they just told us this, which means they told us this. So there's our x and there's our y. All right. Now we need to know the slope at that. So we're trying to think about what that means, and what that means is we need W prime of 3. Going back to what we talked about originally, if we're talking about the flow of water into a tub, then we're talking about accumulation being the volume. So W of t is equal to 0 to t of f of t dt. So this accumulation, right? So that's from 0 to 5, but for our purposes right now, that's all we need. So looking back to the fundamental theorem, W prime of 3 means f of 3. Guarantee this type of transmission, this type of application will without question be on the test. And what that means is we have an integral, and when we take the derivative of that integral, we're actually finding the function at that point. So when we say W prime of 3, we're looking for f of 3. And f of 3 is, well, this is a calculator problem. Now the reason I'm using the whole thing right now is because I don't want to simplify it at this point. Now we have our slope, we have our coordinate point, and we just work it out. So changing y minus this equals my slope. Times that. So there's an equation. There's my linear equation right there. I would probably prefer to simplify it to this value. And I'm again going to put that in my calculator and evaluate it at 3.5. So I'm going to plug that in my calculator. I'm going to evaluate it at 3.5, and what that gives me is 2.952 cubic feet of water at 3.5, at the estimate of 3.5. So there's our linear function right here. We're plugging it into our calculator and we're evaluating it at 3.5, and that's our estimate. Okay? Okay, so if we were aware enough to determine that W prime of 3 is equal to F of 3, then we should be aware enough to know that W second prime of 8 is equal to these functions evaluated at 8. But remember, at 8 minutes, it's both flowing in and leaking out. So generally speaking, we're talking about W of T. And again, we're only writing this because we're in the second stage of this problem. And we're going to go 5 to T. The notation is not absolutely important here, essential here. Okay? And what that means is we're now looking at this from 5 to 10, with T being our unknown. So from 5 to 10, this is the water going into the tub. This is the water leaking out of the tub. And obviously, we're subtracting it because it's leaking, right? We're talking about the total volume, and this is a T here. So now we're looking at W second prime of 8. And what that means is, remember, W prime is simply these two functions. F second prime would be the derivative of these two functions. All right, so we're using the fundamental theorem of calculus to go from originally W prime to F of 3, or W prime of 3 to F of 3, and now we're using it for the second derivative, which is the same process. We just do it again, and we end up with F prime of 8 minus L prime of 8. And we use our calculator here, and we end up with negative 0.183. So what that means is, at time equals 8 minutes, the rate at which the water changes in the volume is the rate of change of the volume of the water is changing by negative 0.183 cubic feet per minute. So there's our worked out problem. You can pause that if you want to look at that. Okay? And I gave you the PDFs of these forms as well. Okay, part C. Is there a time from 5 to 10 at which the rate of change of the volume changes from positive to negative? Give your reason for your answer. So I'm not going to go into what we're talking about is the rate of change of the volume. So here's our rate of change of the volume. It's W prime of T, which is equal to, we already talked about this, Ft minus L of T. And again, because we're looking from 5 to 10, we need to include both functions. All right, so this is what we need to understand. Then our question is, if it goes from positive to negative, it must be 0. So we set it equal to 0. And again, this is our calculator. We literally put these two functions in our calculator. We subtract them, and we find out that at T equals 8.149287, this equals 0. So this is our F of T minus L of T. And if we calc 0 here, we go left bound, we go right bound, we need to be below the x-axis, and we find out that it's 8.149, so on and so forth. So there's our 0. And the question is, specifically, does it go from positive to negative? And the answer is yes, it does go from positive to negative, because W prime is greater than 0 from 5 to 8.149, and W prime is less than 0 from 8.149 to 10. So there's no reason to go into great detail, but you just allow that, just explain that. Okay, part D. The tub is in the shape of a rectangular box that is 0.5 feet wide, 4 feet long, and 3 feet deep. What is the rate of change of the depth of the water at the time the tub is equal to 6? So in this particular problem, we need to recognize it's related rates. So just as we've done before, we determine what's been given. So we have our W equals 0.5, our L equals 4. Again, we don't need to concern ourselves with limits at this point. Our H is our unknown, and our H prime is our question mark. That's what we're looking for. Okay? And then they say at T equals 6, what is the depth of the water? So in this case, we've set up our formula, which is our volume formula, right? In this case, our width, which does not change, is 0.5. Our L, which does not change, is the length and width of a tub, is 4. And our H is our unknown. A little bit of cleaning up gives us our volume to be 2H. All right? And the question is, what is the rate of change of the depth of the water in the time t equals 6? So we find the derivative. V prime equals, in this case, 2H prime. We use implicit differentiation. Now, I used the notation V here for volume, but remember, this is our W prime. So we're specifically looking for 6. Therefore, this is equal to, it's not equal to F prime of 6. It's equal to F of 6 and L of 6. We already have this equation in our calculator, so we want to go to x equals 6, and we find it to be 0.50058. Now remember, this is not our solution because we're looking to set this up. We're looking for H prime, right? So we take this and we plug it into here. Don't do any rounding until you're done with the whole process, and then we divide this answer by 2, and we get 0.250 equals H prime. And that's our solution. So for all 4 of these pieces, they're challenging, but if you make a commitment to what you're doing, if you look at what the process is, they're within your skill set. You just need to be committed to the process.